Hello, everyone. Welcome to our session of supply chain and digitalization. Today is the last day of our ISSD conference. I hope you have enjoyed all the sessions so far. So in this session today, we have two speakers, and also we'll have one more bonus presentation from one international speaker who couldn't present yesterday. So for the two talks related to supply chain, one will talk about the natural gas supply chain and its impact. And the second one, we'll talk about the blockchain and resilience. I think we all know that supply chain plays a very important role in our society. It has direct impact on the effective production of different manufacturing goods and their environmental impact. So I hope this session will give us some insightful discussions on supply chain and all related sustainability questions. So our first speaker is Chen, and she's a fourth-year PhD student in chemical engineering at the University of Texas at Austin. And she works with Professor David Allen. And before coming to UT Austin, she got her bachelor degree in chemical engineering at Dalian University of Technology in China in 2017. And her PhD work focused on life cycle greenhouse gas assessment of natural gas and natural gas co-product supply chains. Currently, she's doing a summer internship with Gas Technology Institute. Qining, it's your floor.
Thank you for the introduction. So after saying hi to everyone, let me stop my video for a better audio delivery.
Yes, we can see that. Thank you.
Yeah, sorry for the delay. And thank you for the introduction. I'm going to introduce some work we've done about the long natural gas supply chain. And this is collaborative work between the University of Texas, Northwestern University, the Process Profiles in California, the NICE American Research also in California, and also the National Institute of Clean and Low Carbon Energy in China. So I'm first going to introduce the increasing growth in global trade of liquefied natural gas, or LNG, which drives the worldwide interest in life cycle assessments of greenhouse gas emissions associated with the natural gas production and the exported and imported natural gas. And to understand the life cycle greenhouse gas emissions associated with these exported and imported gas, the compounded effects of the natural gas involved in the long supply chains become very important. So I'll talk about the compounded effects using several material flow diagrams with our case scenarios. And finally, I'll talk about the impacts of emission modeling from upstream production and then the options of end uses of imported gas on the long supply chain assessments. So let's first look at some background for the global trade in liquefied natural gas. The global LNG industry has experienced a period of significant growth, and there was about 355 million tons of LNG traded globally in the year of 2019, which is about 13% of growth compared to the amount of gas traded globally in 2018. And for the exporters on the left-hand side on this diagram, in 2019, Qatar was the largest LNG exporter in the world, closely followed by Australia and then the United States. And then for the importers on the right-hand side on this diagram, the European countries, Japan and China, have the largest markets. So according to the 2020 gas report by International Energy Agency, such rapid growth in global trades of LNG have been continuous for 5 years by the year of 2019, since 2015. And the global LNG trade is expected to reach close to 600 billion cubic meters. So it's about another 20 to 30% of increase from the amount of gas traded in 2019. And the similar growth pattern is expected in the US as well. As one of the largest natural gas producers and LNG exporters in the world, the trade of LNG has been experiencing a much more significant growth. The LNG exports in US started around the year of 2016, mainly because of the shale revolution in the United States, and it grew almost 13-fold from 2016 to 2020. From less than 1 billion cubic feet per day in the year of 2016 to almost 10 billion cubic feet per day by the end of 2020 after recovering from a significant drop due to COVID-19. So the amount of LNG exported has almost reached the amount of pipeline natural gas exported in the United States. And these exported gas are delivered to over 30 countries and regions worldwide. So with such rapid growth of global trade in LNG, the greenhouse gas emissions associated with natural gas production are getting more and more attention. And methane is the main component of natural gas, with the global warming potential as about 34 to 87 times of equivalent CO2 emissions. And therefore, the methane emissions, primarily from equipment venting and leaks, may offset the climate advantage of using natural gas rather than using the conventional resources like petroleum and coal. The natural gas and petroleum systems is the largest methane emission contributor among all the other methane emission sources in the US, as is showed on the pie chart on the right-hand side. And in addition to the methane emissions, there are also carbon dioxide emissions, primarily from fuel combustion for energy demand, such as the emissions from combusting natural gas to drive compressors in the gathering facilities. And in this work, we'll just focus on the methane emissions. So recognizing the greenhouse gas emissions from upstream natural gas production, the life cycle greenhouse gas emissions associated with liquefied natural gas are also of great interest for both gas producers, gas exporters, and importers worldwide. For example, China, as one of the largest LNG importers, has committed to go carbon neutral by the year of 2060. Therefore, it needs to measure the life cycle greenhouse gas emissions from every energy source imported and used. And similarly, the European Union has set up strategies to reduce energy-related methane emissions to reach the 2030 climate targets and the 2050 climate neutrality goal. And such strategy requires accurate measurements and reporting of methane emissions in methane emission sector, including the energy sector. There are also large industrial interests. For example, the gas producers in the US have volunteered to commit to the Natural Gas Sustainability Initiative, or NGCI. It's an industry-wide approach for companies to calculate the methane emission intensity by measuring and reporting methane emissions throughout the natural gas supply chain. So in terms of the life cycle stages of LNG imported and exported, we can roughly divide them into upstream production, midstream transmission, and downstream uses. And there's great variability in upstream methane emissions among different shale production regions. And the figure on this slide is showing the upstream methane emission factors for some major basins in the United States. So the upstream methane emission factors are defined as the methane emission rates from upstream production normalized by the methane or natural gas production rates. The methane emission factors among different shale basins vary a lot. For example, methane emission factors in the Fayetteville Shale and in Marcellus Shale are only around 0.1%, but in Barnett Shale it's around 1.3%, which is almost 10 times higher than the emission factors in the Marcellus Shale and Fayetteville Shale. And these variabilities among shale basins result in great variabilities in upstream greenhouse gas emission estimates. And the national average is around 2%, which means if we assume a 20-year global warming potential of 84 to 87 CO2 equivalent for the methane emissions, the methane emissions just from the upstream production will have an impact equivalent to over 50% of emissions from combusting this methane. So that's quite a lot. Methane emissions will also be a large fraction of the life cycle greenhouse gas emissions of the exported and imported gas. So in addition to the emissions from upstream production that I just showed, the methane venting and leaks and uses from other life cycle stages like ocean transport, liquefaction, regasification are also not ignorable. And the life cycle assessments of greenhouse gas emissions of exported and imported natural gas involving long supply chains needs quantifying the compounds and emissions in every life cycle stages along this long supply chain. For example, here we have a case scenario showing the life cycle stages in the long supply chain involving natural gas source from the United States for power generation in China. Gas is produced from the wellhead in the United States, then gathered by the gathering facilities and sent to the gas processing plants where natural gas and natural gas liquids are separated and pipeline quality natural gas is produced. Then the pipeline quality natural gas is then transmitted by these transmission pipelines to a liquefaction terminal to be compressed to the liquefied natural gas. Then the LNG is delivered to China via ocean transport and will be regasified in the regasification terminal near a port in China. Then the gas is transmitted again in China to the end users or the power generation plants. And for this long supply chain, there are a lot of gas consumed and lost along the supply chain, and the gas extracted from the wellhead is obviously not equal to the gas delivered to the power plant. But it's not very clear how large the gas losses will be and how large the impacts of gas losses and the uses will have on the overall supply chain. So here we have a table summarizing the components of gas consumed and lost along the long supply chain. There are fugitive emissions like equipment leaks from almost every life cycle stage along the long supply chain, and the same happened to the vented gas. And then most of the stages require some natural gas extracted as fuel to power the equipment, and this is another source of gas loss or use. In the upstream production and processing, there's also some gas flared because there's not enough infrastructure to process those gas or just due to some operation needs. So it's another type of gas loss along the supply chain. So with this background, here are the goals for the rest of this presentation. Well, first, map the variability of gas consumed and losses along the long supply chain from US to China using two case scenarios with natural gas sourced from two regions in the US with very different production characteristics. Then we'll assume a couple of options for end uses for the imported natural gas in China to quantify the compounded effects of the supply chain and natural gas. And finally, I'll introduce some additional work we've done before on assessing the impacts of the emission allocation methodology in the upstream production. So this is our first case production region. It's the East Texas Basin. It's one of the foremost producing basins in the United States with about 130 years of production history. And it has several formations stretching across the northeastern of East Texas and West Louisiana. And currently it's mainly a dry gas production region with about 1,200 billion cubic feet of gas produced per year. And here's our second case production region. It's the Permian Basin located in West Texas and the joining region of southeastern of New Mexico. It's one of the largest oil and gas producing basins in the United States with over 180,000 oil and gas producing wells, which accounts for over 30% of oil production in the United States. The gas production in the Permian Basin per year is around 4,000 billion cubic feet. So it's nearly 4 times of the gas production in the East Texas Basin. And very different from the production in the East Texas Basin, the Permian Basin is a relatively wet region with a large amount of oil production at the same time. So it produces about 1 gigabarrels of oil per year. So with very different upstream production characteristics, the gas use and losses over the long supply chains could be very different between the Permian Basin and the East Texas Basin. And another thing worthwhile to note is that the Permian Basin is the US oil and gas region with the largest reporting methane emission flux. So we can assume that some methane lost as the form of methane emissions in the Permian Basin, and those should be higher than in the other regions. So these two regions, the East Texas Basin and the Permian Basin, will be used to map the gas consumed and losses along the long natural gas supply chains. And we also have a third case production region, is the Eagle Ford Shale in Texas. It's located in South Central Texas with over 24,000 oil and gas producing wells. It produces around 2,000 billion cubic feet of gas per year, so less than the Permian Basin, but it's still one of the largest gas producing regions in the United States, and it produces about 350 million barrels of oil per year. So the most interesting with the Eagle Ford Shale is that it covers a wide range of production characteristics, including oil production, gas and condensate production in the middle of the region, so oil production in the northwest of the region, and also it has dry gas production regions in the southeast of the region. So due to these production characteristics, in our previous work, the Eagle Ford Shale was divided into 12 production subregions based on the API gravity of the liquid produced, so it's just how heavy the liquids are, and the gas to oil ratios of the wells. And the Eagle Ford Shale, since it's a very representative region covering a wide range of production, is used to demonstrate the allocation issues in the upstream production. So let's first look at the mass flow diagram from wellhead to power plant for a dry gas region, and the gas is sourced from the East Texas Basin. So due to the gas consumption and losses along the natural gas supply chain, the mass of hydrocarbons extracted at wellhead is about 50% higher than the mass delivered to the power plant. And the mass is mostly lost to the combustion. For example, some natural gas is extracted and combusted during the supply chain to drive the compressors along the gas transmission or gas gathering pipelines. And some of the natural gas is just flared due to operation needs. The combustion loss accounts for 65% of the total mass loss from this long supply chain, and it's followed by the co-products. So natural gas liquids are separated from the wellhead gas and used elsewhere, which accounts for about 25% of the total mass loss from the long supply chain. Then the gas storage and injection accounts for another 5% of mass loss, followed by emissions accounting for 4% of mass loss. So again, to remind you, this mass flow diagram is quantified for the supply chain with natural gas sourced from the East Texas Basin, which is a relatively dry gas region with few co-products and fewer emissions. But the Permian Basin will tell a completely different story. Still looking at producing 1 megawatt-hour electricity in a power plant in China with gas imported from the United States. The mass of hydrocarbons extracted from wellhead is over 200% higher than the mass delivered to the power plant. And of these mass losses, 45% of the mass is lost to the co-products, including the natural gas liquids and the large amounts of condensate oil, since the Permian Basin is a relatively wet region compared to the East Texas Basin. The co-product uses is followed by combustion, which accounts for another 30% of the total mass loss, then followed by the storage and injection accounting for another 12% of the total mass loss, and emissions accounts for 8%, and hydrocarbon gas removal accounts for 5%, because in the Permian Basin, the gas are less pure. So the fraction of gas lost due to emissions in the Permian is also higher than the fraction in the East Texas Basin because of the existing of a large number of oil-associated equipment like condensate tanks in the Permian Basin with high emission intensities compared to those equipment associated with only gas production like in the East Texas Basin. So to summarize the above results, the changes in gas flow to end users will create gas flows at wellhead that are between 50% and over 200% larger at the wellhead, depending on where the gases are sourced from. And this leads to corresponding increases in emission estimates of the gas used at the end. So if we look at the Permian case, a change in gas use in the power plant will lead to produced gas flow at the wellhead in the Permian Basin that is 3 times larger. And less than half of the increased flow are the co-products. Therefore, the accurate mass flow tracking from production to gas processing is even more important. And as we just summarized, the change in end uses of the gas can be scaled up due to the compounding effects. So the choice of end uses in long supply chains also matter. So let's look at the same scenario, but with more details, with a couple of different assumptions in the life cycle stages in China. So we still have this gas produced from the wellhead in the United States, going through all the upstream and midstream stages to the regasification terminal in China. Then the imported gas coming out of the regasification terminal near the port where LNG is received can either be transmitted to power plant at other locations, represented by the cases A and B on this diagram, or be used at the power generation plant locally, represented by the case C. So for cases A and B, where the imported gas is transmitted, the transmission of the imported gas can either be powered by some of the imported gas itself, which is a common practice, represented by the case A, or it can be powered by the local gas in China, represented by case B. For the case C, where imported gas is used at the power generation plant locally, the electricity coming out of the power generation plant can either be used locally at where the power generation plant is, or transmitted via the electricity transmission lines to end users at other locations in China. And to give you a more detailed geographical information, the imported liquefied natural gas is transported from the US to Shanghai port in eastern China, and end users are assumed in Shandong province, which is roughly 800 kilometers from Shanghai, or in Liaoning province, which is roughly over 1,700 kilometers from Shanghai. The transmission losses of both electricity and gas are considered over these transmission distance. So in more details, here are the four scenarios. The first scenario will only transmit the imported gas. So the imported gas is transmitted from the regasification terminal near Shanghai to a power plant in Liaoning or Shandong province. And then the electricity is generated and used in regions close to the power plant. So we assume no further electricity transmission. Under this scenario, the first case is that the gas transmission in China is powered by the imported gas itself. And the second case is that gas transmission in China is powered by the local gas in China. And in the second scenario, we don't transmit the imported gas, but instead the electricity is generated in the power plant close to the regasification terminal near Shanghai. And under this scenario, the third case is that the electricity is used locally in Shanghai, so there's no electricity transmission. And the last case is that the electricity is transmitted to end users in Liaoning or in Shandong province in China. So we quantified the amount of gas required from wellhead in the Permian or in East Texas to produce 1 megawatt-hour electricity in China with the previous 4 scenarios. The blue bars represent the Permian case, and the green bars represent the East Texas case. And based on our previous analysis in mass flows, it requires less wellhead gas if gas is sourced from the East Texas Basin compared to if the gas is sourced from the Permian Basin for all the case scenarios. So if you look at the first cluster of the bars, it represents our first case in which the imported gas is transmitted from Shanghai to Shandong or from Shanghai to Liaoning, powered by the imported gas itself. And the second cluster of bars represent our second case, so the same scenario as the first case, but the gas transmission in China is powered by the local gas in China. So comparing the second case to the first case, combusting local gas, if there is some gas available, would be a better choice and will require less gas imported, therefore less emissions associated with the gas used. And if local gas is not available for power gas transmission and combusting the imported gas is needed, shorter distance of gas transmission would be preferred. So, for example, in this case, the power generation and the end uses in Liaoning, which is further from Shanghai, represented by the second light blue bar in the first bar cluster, requires 5% more of gas from the Permian wellhead compared to the power generation and uses in Shandong, represented by the darker blue bar in the first bar cluster. And the third and fourth clusters of bars represent our third and fourth cases in which gas imported are not transmitted further, but are used to generate electricity locally near the Shanghai port. And the electricity is transmitted to Liaoning or Shandong province for end uses or just used locally. So if you compare the third and fourth cases with the previous two cases, there isn't really a strong preference on transmitting gas or generating electricity locally and transmitting electricity, just in terms of the amount of gas required from the wellhead. And the final piece of work I want to introduce briefly is regarding the emission allocation choices in the upstream production. So here I have a diagram showing the typical flow and system boundary of the upstream oil and gas production. So the well stream extracted from wellhead was sent to the separator, separated into produced gas stream, condensate oil stream, and the water stream. Then the produced gas stream, which we care most, are gathered by the gathering facilities and sent to the gas processing plants where natural gas and natural gas liquids are separated. And then the condensate oil stream is sent to the condensate tanks as oil products. So inside this system boundary, we have both natural gas liquids, and oil products. And we have greenhouse gas emissions associated with all these co-product production. So the allocation choices inside this system boundary will have a large impact on the total greenhouse gas emissions assigned to the natural gas. However, the mass flows in production through gas processing are very complex and are rarely modeled in detail. So they can have significant impacts on results, but also result in a lot of uncertainties. So how to allocate methane emissions inside this system boundary between these co-products become very important issues. And in our previous study, we have assumed 3 scenarios. In the first scenario, we assign all the emissions inside the system boundary I just showed to the natural gas products because it's the product that we care most. And in the second scenario, we assign those emissions to both natural gas and natural gas liquids because sometimes natural gas liquids are also used as a part of co-products. And in the third scenario, we assign emissions to all the products, which makes more sense because those emissions are associated with both gas and oil production, but it's a less common practice. And we apply these 3 scenarios in the Eagle Ford Shale that I introduced previously, which cover a wide range of production characteristics from oil production regions to dry gas production regions. And we found that the differences in natural gas emissions due to allocation choices are more significant in wet gas and oil regions than in the dry gas regions. And in the most extreme case, so in oil production region 1, the differences in emissions allocated to natural gas can be like tenfold between allocation scenario 1 and allocation scenario number 3. And here I listed a couple of work related to the allocation study we've done before, if you're interested. Then in conclusion, recently the increasing growth in global trade of natural gas and liquefied natural gas have driven great interest in life cycle assessments of greenhouse gas associated with the exported and imported gas. However, there are non-trivial portion of gases consumed and lost along the long supply chain, and they are not accurately measured. But quantifying the mass flow along the long supply chains is very critical in the life cycle assessment of greenhouse gas emissions of those exported or imported gases. Also, those compounded effects and the emission assessments can be affected by the emission modeling methodology, like the allocation method from upstream production, as well as the end-use choices for the imported natural gas at the end of the long supply chain. So that concludes all my work. Thank you. And all the questions are welcome.
Okay, all right, Qining, thanks for your presentation. It's really insightful to look at, compare the upstream and downstream impact of the natural gas. So while we're waiting for any question from the audience, I guess I can start with just a few questions. Yeah, so one of my questions, it seems like your results shows that the variations in the upstream are much larger than the variations, the impact are much larger than the impact of variations in the downstream, like the in China. So then at the end, you talk about the different allocation choices. I'm wondering if you use different allocation method, whether the comparative result of upstream and downstream will be different.
So do you mean using different allocations in both upstream and downstream production?
Just in upstream, because basically your previous result shows that emissions, all these emissions in the upstream, if you get natural gas from different places in the US, they have a much larger impact than those variations when they import it into China, right?
Yeah,
and for those fugitive emissions, you also need to allocate them, like fugitive emission or vented gas. You also need to allocate them to the natural gas and natural gas liquid, right? So I'm just wondering whether if you use different allocation method, whether this upstream downstream comparison will be different.
Yeah, we have not yet aggregate the upstream allocation work into this long supply chain study. So that's why I'm showing like the previous work we've done. But after this long supply chain study, it's a good point to aggregate those upstream allocations to see how it will affect the end users and the overall supply chain. Yeah, it's a very good point. Thank you.
Yeah. Let me see whether there are any questions from audience. Yeah. Not yet. I guess my another question is, you talk about like those losses can be from like 50% to the 200%.
Yeah.
Very large, right? I remember many years ago when I did the life cycle assessment for the ethylene, which is a petrochemical produced, mainly produced from natural gas in the United States. This upstream loss and fugitive emission can be really huge. So I'm wondering whether you can comment on any effective measures to reduce those lost during the entire long supply chain in order to reduce like methane emissions, especially given they have large impact on the climate change and global warming.
Yeah, so if we are able to measure the emissions at the equipment base, equipment by equipment, we'll be able to quantify the emissions from each equipment in every life cycle stage, and from those emissions, we can use the mass balance to calculate how much mass is lost along the supply chain. And another way I don't think is very feasible is to measure the amount of gas throughput at each stage. But like in the ocean transport and regasification, liquefaction, at those stages, it's not very possible to measure those gas throughput at every stage. Yeah, so I think like measuring the loss from the view of emissions would be a good way.
Okay, all right. So thank you very much for the very nice talk. If there are no other questions from the audience, I would like to thank you again and also invite our second speaker to be on the stage. So our second speaker is Nallapaneni Manuel Kumar, and apology for my pronunciation. I'm sure it must be wrong. But our second speaker is a PhD student at the School of Energy and Environment, City University of Hong Kong. And his PhD thesis is on leveraging blockchain and smart contract technology for sustainability and resilience of circular economy business models. And the talk will cover, that topic cover business cases like battery swapping charging stations, material passport of e-waste, industry symbiosis, etc. And his current research interest is building integrated photovoltaics, sustainability, resilience, circular economy, smart grid, techno-economic analysis, and also life cycle assessment. So without further ado, I will pass it over to our second speaker. It's your floor. Yes, we can see your slides now. Thank you.
Thank you for the introduction. I think my presentation is quite different from the rest of the presenters, but still I'll make it very simple. So I think most of us are familiar with the concept of linear economy, and most of the industrial facilities have been operating using this business model maybe since decades. And under this business models, we face a lot of concerns, and mainly these concerns comes from raw material extraction point of view, and even in the production phase, and even in the use phase. So it is always advised to have limited resource extractions, considering the environmental impacts, and even other side, the energy used in the manufacturing of various products. So the next transition is about to have a circular economy. So CE at its core ensures circularization of resources, and it mainly focuses on recycling measures and efficiency improvements and use phase extension and a more intensive use phase of the products. And it even suggests us to have a product by a service or software solution. So this is more or less covering the aspects of dematerializing the products or components or materials we use. Instead, we promote product as a service business model. So now, in order to implement the circular economy, we need to have different business models. Let us have a look what exactly these business models look like. Uh, So currently we have like 5 different business models, and these 5 you can see like the resource recovery, circular supplies, product life extension, sharing platforms, and product as a service. And these 5 business models are mapped here to a particular product life cycle. And in today's presentation, we will more concentrate on, excuse me. So we'll more concentrate on a business model that is circular supplies. I think my mouse is not working. Can you able to see my screen? Yeah. I think in today's presentation, we will see the business models that is circular supplies. So what exactly the circular supplies business model means? So circular supplies business model aims at reducing the use of virgin resources, and its primary focus is to have alternatives for virgin resources used in the manufacturing process or even any other activity throughout the life cycle. And resources with renewable nature, degradable nature, recyclable or reused nature are perfect fit for this business model. And the value proportion of this business model will revolve around the activity that is happening within the business model. And now let us see what exactly the circular energy supplies. So I think the more or less the circular energy supplies we can see in industrial symbiosis concepts. And traditionally, we have industries that are not coexisted, and more or less 1 or 2 industries might having a share, might exchange waste resources. So that we can see from the right-hand side top figure. But if you see from a circularity point of view, the level of circularity, what we see in the first figure, is not high. So to promote circularity, it is always advised to have uh, industries to have like more exchanges. So it is more or less talking about having a maximum number of synergetic collaborations. So like how you see in the second figure. So now among the waste streams, energy is also one of the waste stream which we can see nowadays. And these energy sources are in different forms. Say for example, natural gas, heat, electricity, steam, and others. Now, when we have an industries that have synergies between different firms and they were able to exchange these different forms of energy, such symbiosis concepts can be called as industrial symbiosis based multi-energy systems. And now, what exactly the challenge in this industrial symbiosis based multi-energy systems? Now, if you see a real-time example that is implemented in Kalundborg in Denmark, so its practical implementation is quite questionable, especially when we consider the disruptive scenarios. And more or less, if one firm experiencing a disruption, there is a chance for it spread onto the other industries. So this is something similar to cascading failures, which would emerge from one firm to another. So such scenarios would make the entire system, that is, entire system, not having a resilience. And the other side, the resilience have a direct linkage with the sustainability of the overall industrial symbiosis network. Now let us see what exactly the relation between resilience and sustainability. Now, if you see this particular figure, on the x-axis we have the time, on the y-axis we have a sustainability. So now in the industrial symbiosis concepts, when they're trading waste energy between one firm to another firm, so they're not dependent on a virgin energy resources. So that's more or less they're trying to reduce the emissions that would release if they wanted to have energy that is generated from a fresh resource. So in that way, the sustainability value of that particular network would trend to increase, But whenever there is a case of disruption, so what happens is one firm will failure and the amount of energy that has to be supplied by it will be stopped. Then this industry has to depend on a real market or some other industry, or it has to depend from a primary energy source. So in that case, what is happening is the sustainability value of the overall system will drop down. And the sustainability will drop down and continues to drop down unless the system is recovered and the failure is mitigated. But to understand the resilience, what exactly we need to have it. So in this case, it is always advised to have a step-by-step approach, understand what is happening at each phase of this circular energy supplies activity. So now we have a framework that will inform us the decisions throughout its life cycle. So now when you see this particular figure on the right hand side, so this figure has it is a time bound figure and it has different components of time that is having relationship with the functionality. So here the functionality is a component of sustainability as well as the resilience. But first let us have a look at only the resilience aspect, as we already discussed the sustainability in the previous figure. So now assume that at t is equals to 0 time, the system has 100% resilience. That means there is no fault. But at t is equals to 1, the system starts to fail, and at t is equals to 0, the system is completely failed. And at t is equals to 3, the system is again rebound. At t is equals to 4, the system is adapted to such faults. So that means the entire resilience of the system can be understood by using these 4 different phases. There's a preparedness, robustness, recovery, and adaptation. Now, what exactly the preparedness is? So preparedness informs us about the failures in a prior intimation itself. So then the system can have decisions whether it can procure energy resources from a neighboring firm or from a different marketplace. And the robustness will inform us to what level the system can survive for its failure. And the recovery is the time taken to rebound or to come back to its original preparedness level. And the adaptation is giving us the information how the system is learning from its failures. This is the typical challenge we face in the current industrial symbiosis concepts. And if you see these challenges in a more detailed way, so these are the 2 challenges we have. Finding a suitable partner for energy exchange is quite difficult because it always involves negotiations on prices, and it even involves the supply chain aspects and the mobility aspects. And on the other side, we are not sure that the firm we requested for energy is providing the same quantity are the same quality of energy resource that we are seeking in the industrial facility. So now, what is the ultimate solution for this? The ultimate solution is to depend on a marketplace, and this marketplace has to have a set of rules and guidelines, especially for energy resource trading. And now the question is, should we depend on a conventional marketplace or should we go for a digital? And on the other side, the system that allow a firm to have prior information regarding disruptive events. So this is always comes with having a lot of data and predictive analysis about different failures. Now, in the recent literature published by a research group in University of Twente, they have suggested the use of online information sharing platforms in order to understand the overall performance of industrial symbiosis networks. And now here I'm talking about online information sharing platforms. That means these platforms will not come without without having a proper knowledge on various digital technologies. And these technologies would look something like this. So we need to have like Internet of Things, artificial intelligence, big data, and even the more advanced technologies, that is distributed ledger technologies. So now, how do you integrate all these systems in an industrial symbiosis concept is a big question. And on the other side, we still have a question that a CA research is going digital. Now, when we see a recent project that is granted under NSF, so we have a collaborative research project on convergence around circular economy that is more talking about applying digital tools on creating material passports for electronic waste. And we even have corporates talking about how circular economy would use the digital technologies. And in recently, European Union's Circular Economy Research Alliance has also stepped into this digital circular economy concepts. And even we have the circular economy stakeholder platform is talking about having policies and regulatory measures on digital tools and circular economy. So everyone are talking about going digital with circular economy concepts. But how do you transform? How do you transition is a big question mark. Now, for this, let us understand what exactly the recipe for circular economy transformation. So now, if you see this, so there are a bunch of digital technologies which we can use in circular economy transformation. But all these technologies might be applicable in different phases of a product or a component life cycle. But more from a circular economy point of view or from an industrial symbiosis point of view, we need the technologies that are highlighted in the red color box. And in today's presentation, we will more look at how blockchain can be leveraged in industrial symbiosis concepts. And the objectives are here like this: to conceptualize and develop a blockchain-based online information sharing platform for ISMES, and to model a firm-to-firm IS relationship, establishing mechanisms following IS principles through blockchain-based smart contracts. And the third objective is to quantify and compare the resilience of ISMES in business as usual scenario, as well as the BIOS scenario we have it. So first, let us understand what is blockchain and smart contracts. So let me make it very simple. The blockchain is another database what we have right now. It's more or less the storing data in different drives. But what blockchain offers is it stores the information in a distributed nature, and it keeps track of transactions that happen between the parties in the whole CE network and protects them from tampering. And in addition, it also allows P2P interaction and helps in improving trust between them by providing verification facility. And now we have a typical structure of blockchain on the left-hand figure. Upon each transaction, how information is stored here. Each transaction information is stored in one block, and all the blocks are connected together like a chain. Another side, what is a smart contract? Smart contracts are nothing but your conventional contracts, like how we have a rental contracts between a tenant and the landlord. A similar way here also we have a contracts between different stakeholders in CE, but these contracts are written on a blockchain digital scale. Now let us understand what exactly the role of blockchain technology in CE. Assume that two stakeholders are having a transaction, a circular economy transaction, like they're having an exchange of a natural gas or exchange of other energy resource between them. Now, in that cases, they mostly have challenges. For example, a data ownership. Maybe a first stakeholder might say that I have already transferred all the energy resource what you have requested for, but he might have quoted a different price, different quantities on a paper. On the other side, we even have issues with data sharing, issues on trust between the quality and the quantity they are exchanging. On the other side, the transparency again matters. But now, if you apply a blockchain for the same particular transaction would something look like this. The stakeholder would initiate a transaction, then a security signature with all the information that is to be shared between the stakeholders will be ensured here. Then the whole transaction is shared between the parties, like in IS. Not only these particular two stakeholders, there are other stakeholders, including the regulatory and including the management systems and everything. So everyone has to approve that particular transaction. Once it is authenticated, that particular transaction is stored on a digital database, and then a virtual transaction will happen. And as per the virtual transaction, on the other side, through mobility, we will have a physical transaction would happen. And now let us develop a circular economy blockchain considering the core principles of circular economy and the core principles of blockchain. And on the right hand side, we see a simple circular economy, circular business model, and the same circular business model considering different stakeholders and their roles in the entire life cycle of this particular business model. So we will have different decisions. And the first step in the circular economy blockchain architecture is what exactly the circular economy service we are going to offer and what sort of transactions each stakeholder should have it. Then we will ask the stakeholders to register on this platform. Then we will define the connections between each stakeholder, and we even provide their what sort of rights each stakeholder have it, either in terms of data or either in terms of data disclosure or either in terms of exchanges. Then once we have all these things, then we will select a blockchain platform. Then we will write the consensus, and here we write all the contracts that exist between each stakeholder. And this way we can have a circular economy blockchain platform that is developed. And once this platform is developed, and we will ask all the stakeholders to register, and the registration process would follow these particular 6 different steps. And in each stage of exchange, all the 6 stages will be executed. And now let us see how this information platform would look for a user interface. Now here is a 3-node problem I have shown here. Now let us assume that an industrial symbiosis network that is existed, and they have 3 forms in the total network, F1, F2, and F3, and they are having synergies between them. And now all these 3 forms will be registered under a physical layer. So whoever have excess supply of energy or who wants to be participants in this industrial symbiosis concept will be registered under a physical layer, and whichever firm which is vulnerable to some sort of disruptions will search for a suitable energy exchange partner through the searching layer. And then once the searching layer, they are searching for a suitable partners, and once they found out, based on the written smart contracts on a blockchain, we will execute the transaction, and this transaction will enable them to have a physical flow of energies. And now the developed platform is tested on a simulation bed, considering Kaulenberg industrial symbiosis as a case study. But in Kaulenberg industrial symbiosis, energy, water, and materials are traded. But a simplicity purpose here, we just considered only energy supplies. And the other side, as we already discussed, the current topic is concentrated on a business model that is circular energy supplies. And now, considering only the energy supplies, we rearrange the network, and this total network has 5 different energy streams, that is stream, power to grid, warm condensate, and district heating, and natural gas. Now, how these industries will trade even in the case of disruption is the question, and how resilience is ensured in the whole network, we will see in the coming slides. Now, the methodology we adapted here is we have considered the 4 components of resilience cycle that is discussed in earlier slides. And as per these 4 components, we have selected few indicators. And for the preparedness concept, we have considered an indicator called Gini coefficient and degree centrality. So this Gini coefficient is mostly used by economists, and even in terms of evaluating GDP of any nation, we use this particular coefficient. And the same coefficient is used here in evaluating the preparedness here. And now Gini coefficient is used to understand and have the predictive capability of the consequence in the case of random failure, considering the whole network. And then the degree centrality metrics, what we use here, will inform us how important each firm in terms of attaining the overall resilience. And the robustness case is simulated considering successive random firm failures. And this process is repeated for a number of iterations to see the level of this net, to see to what level the network can withstand. And then we even have recovery. The recovery is mainly ensured by having a firm-to-firm relationship using the mechanism that is shown in physical searching and execution layers in the earlier slides. And then for the adaptation, we still use the Gini coefficients. And here, the Gini coefficient should be, the Gini coefficients of adapted network should be higher than the Gini coefficients what we have seen in the preparedness. Then we say that the adaptation of the network is achieved. Now let us see the results of this network. And now the first we have the preparedness results, which is the first component of the resilience cycle. And for the entire, for the Kaulenberg industrial symbiosis energy network, the observed Gini coefficient is 0.2386. But when you see the range of Gini coefficient, which is generally varied between 0 to 1, 0 indicates that the network is equally distributed. That means the network have more chances for being resilient. But in our case, it is not 100% resilience, and still there is a chance for failures. And this particular ratio will inform us that the system is vulnerable to failures, and we need to be prepared for mitigative measures. And on the other side, which firm is more vulnerable and which firm is more important in terms of having robustness, or even can have a scope for recovery. So that is observed using the degree centrality. And the observed degree centrality was very high only for Novo Nordisk and Novozymes Land Association Authority. And here it is 0.6. And the next important node is Kaulenberg utility, and the least important firm is Kaulenberg utility heat pump. And let us see the robustness results of this particular network. Now, as I already mentioned, that robustness is simulated by having a random failures, a successive random failures. As per the network shown on the right-hand side, what we did is we removed each firm, and then we restructure the entire network, and we understand the overall robustness of the network and how this robustness can be improved by using blockchain. And what we observed is the blockchain-empowered online information sharing platform will allow the network to be more stable to such disruptions, and the robustness is ensured. But however, the platform fails to ensure that the system is 100% stable or 100% resilient. Now for this, so we wanted to have one step ahead and understand what sort of recovery methods we can employ and whether the system is able to recover or not for such events. Now here, so the recovery is evaluated specific to each firm. And now in these 4 graphs represents the recovery of 4 different firms in the total network. And if you see the first figure, we don't observe any recovery. The main reason is this particular firm doesn't have much importance and its synergetic relations are not much. So if some disruption occurs, what happens is it does not have any synergetic relationship. Hence, there is a more scope for failure and there is no chance for having recovery. And the recovery has to be from a third-party service or from an external layers. So which we will discuss further in the adaptation stage in the coming up results. But when we see GIPROC, so we observed a slight recovery, and the same can be observed for Kaulenberg bioenergy system, and the same can be observed for Kaulenberg utility. And now we have the similar results for other firms here, and here also Kaulenberg utility pump, we did not observe any recovery, and the same thing with Novo Nordisk, and the same thing with Novo Nordisk and Novozymes, and for Novozymes also the same thing. But when we see the Novozymes wastewater and biogas, we observed a slight recovery. And overall, what we observed is recovery was only possible in the firms that has multiple relationships for the same waste energy stream. But in our case, we have different energy streams, and one cannot replace one energy stream with other streams. So that's the reason we did not have much of recovery here. But now let us see the adaptation results. So in the adaptation also, what we did is we have simulated the whole network by applying successive random failures at each network. Now, if you see the diagonal elements represents that particular node is removed at each iterative step of the simulation process. And now, when we remove this KU, that is Kaulenberg utility, what is happening is the observed Gini coefficient is 0.24, which is higher than the Gini coefficients what we observed at the preparedness measure. And on the other side, what we have is Kaulenberg utility have a same energy resource that is coming from 3 other firms in the total network. So when we try to create some buffer energy storages at each firm, and still we observe the restructured network's Gini coefficient, but still we were unable to ensure that the Gini coefficient is lesser than the Gini coefficients what we observed at the preparedness. And the same we have seen for all other networks. And in total, what we observed is there is no improvement in the Gini coefficient when we compare with the preparedness value. But what we observed is there is one particular firm which has the lower Gini value that is even lesser than the preparedness measures, that is 0.19. So this is Kaulenberg utility heat pump. And here, this particular node doesn't have any relationships, and it is entirely dependent on the utility grid, the power grid. And power grid is always connected. So that's the reason we have a bit of adaptation possible for this particular firm. Now, in conclusion, what we observe is it is understood that the proposed BEOS platform has a clear potential to establish synergetic relationship between the firms. However, this is limited only with the buffer capacities they have it. And the other side, there is a possibility for adaptation when a new additional firm or a source of energy is existed after a self-recovery of the ISMES. But in the considered ISMES, the adaptation was not easy, even after having BAS support for a dynamic exchanges of energy. This is mainly due to lack of infrastructure facility in the context of multi-energy. So that means we need to create an infrastructure to procure that particular energy source from outside of the network. And the future work will be on quantification of ISMES adaptation by creating mock energy infrastructure facilities, and even on understanding the role of mobility services and other affecting parameters on the recovery of ISMES, because time is very a crucial parameter in terms of recovery process. And other side, impact of resilience mitigative measures on overall sustainability and economics of this ISMES model. And thank you. I conclude my presentation here.
All right, thank you. I think this is the second talk I heard about blockchain. It's ISSD conference. Really learned a lot. That's very interesting. Yeah. I think before we are waiting for questions, I actually have a few questions.
Yeah, please go ahead.
The question is about, like, you showed a case study of the Kunlinberg, right?
Yes, yes.
I think that seems to be an eco-industry park where most of the facilities are quite close to each other.
Yes.
So I think I have heard that some of the potential of blockchain is really allow this exchange with the form over long distance.
Yeah, over a long distance it is always possible. But how quickly can we have this synergetic relationship is a big question. Because whenever a firm needs energy, and immediately they may not supply it, and it might need to be transported from one location to other location, and this is always a big issue with supply chain, right? And we need to have a logistics here, and whether we will have this energy sent to the particular eco-industrial park on time or not is a big question. Sometimes they might delay. If we delay, the recovery cannot be ensured immediately. So that's the reason we don't see much recovery for some networks. So instead, we propose to have buffer capacities at each network, so that by the time the energy is transported from one location to other location, they can still rely on the buffer capacity, and the industrial activity would not be shut down.
Yeah, I guess my question is on, like, for energy, it's very different because it's really hard to transport over long distance. And for many eco-industry parks, they already have those energy exchange network. I'm just wondering whether your work can be applied to, like, for example, other materials. That's waste material can be transported over long distance, which will not have the energy problem, but your blockchain platform could be very helpful. So would you comment on that?
Yes, actually, we have applied the same blockchain platform for even energy network and water network, but I haven't showed those results here. But those results are included in my thesis.
Okay. All right. So that sounds really interesting. I hope that one day maybe you will have a startup company that's really put your blockchain platform into the market. I think that will make a huge impact. Thank you. If no any other questions, I want to thank everybody to attend our session today. We do have some time that we want to play an additional presentation, which couldn't present from yesterday because of he or she is an international speaker and have some internet problems. So Beth, do you want to be on the stage and introduce that talk so you can play the video? Okay, all right, thank you.
Hi, everybody, and thanks so much for that great presentation. So we do have a speaker who's based in India who sadly had connectivity issues when he tried to present on Tuesday. So he recorded his presentation. It's about 30 minutes. So if you want to stick around and listen, that would be great. I'm sure he'd appreciate it. It is Dr. Suman Devadula. He's associate professor and head of the MIT World Peace University in India. So the title of his talk is Handicrafts for Sustainability Through Promotion of Self-reliant Craftsmanship. So, all right, I'll go ahead and play that and stick around and listen if you'd like. Thank you.
Good morning, everybody. Myself and Dr. Rashmi Munshi will be presenting our work for Handicrafts for Sustainability through Promotion of Self-reliant Craftsmanship. This is largely based on the work that I have done with respect to sustainability and technology understanding, and what Dr. Rashmi has done in her studies, craft studies in Channapatna of Karnataka in southern India. I would like to start with the quote from Alfred J. Lotka. He said that the influence of man as the most successful species in the competitive struggle seems to have been to accelerate the circulation of matter through the life cycle, both by enlarging the wheel and causing it to spin faster. So this is very important to recall at a point where we are talking about increasing use of resources by increasing number of people, and the trend to be reversing for sustainability to be affected or even realized sooner or later. Now, when we come to handicrafts, we're talking about a lot of varieties. Even just in India, we have 35,000 plus different types of handicraft products that India exports to world markets. What you see is beads work, marble work, rattan work, plant fiber work, animal fiber work. Several of these come under the classification called handicrafts. As a representative segment, it is very interesting to see the home decor market. Even in the US, it is considered to be a representative segment of the entire handicrafts market. Now, it is projected by the Allied Market Research Group that the global home decor market is expected to reach $838 billion by 2027, 6 years from now. And the compounded annual growth rate is at 4% in the period 2020 to 2027, which is projected. And the story of India is almost like 15 to 20% CAGR over the past few years, although 2020 is an exception. Now, in particular, just the US home decor market is almost 158 billion by 2027. It's expected to rise from current standards to 8% to 158 billion. That's a lot of market. We are talking, when we talk about the home accessory market, we're looking at the following sectors. We're looking at accessories and gifts, soft goods, accent furniture, portable lamps, rugs, tabletop accessories, lighting fixtures, etc. So a good amount of percentage is on accent furniture, accessories, and portable lamps. Coming to the context of India, India is the largest producer of handicrafts, and it's almost equal in numbers with China, although China produces more machine-made goods under the word handicrafts. So the cultural diversity and heritage is the wealth that we have, and every state almost has quite a number of varieties of crafts on an average, and there are several people generally on the lower strata of income in the societies who survive on handicrafts as a family business. And the export of handicrafts from India is expected to be touching 3.5 to 4 billion by the financial year 2020 as a projection. So this has just closed, but the pandemic has affected the revenues over here, although the projection is true. India's contribution to the world market is 1.2%, and the handicraft industry share in India's exports is just 1.5%. Now that is the size of the economy as well as the share with respect to the world's market for handicrafts. And it is notable that US has 35% share of imports from India. Handicraft has largely been a family occupation inside India, and several people in the family, including women, depending upon the craft and the work involved, are involved in it as a family occupation. It's a major source of earning and livelihood for several families in rural India. The paper also touches on the essential part called craftsmanship, and we say that unless craftsmanship exists, there is no point in meeting the goals, which is about getting a product which is desirable as well as lasting. So skill in a particular craft or the quality of design and work shown in something made by hand is what we subscribe to as the definition for craftsmanship. However, as an interpretation, we want it to be perceived as a capability, a skill level of the craftsman to conceive and effect an acceptable and delightful outcome within given resources. Now, in this sense, it is connected with the amount of control that the craftsman has on the amount of resources that he has access to in realizing the outcomes, which is the craft product in the end. Coming to our understanding of sustainability, we retain the original context of sustainable development, and we define sustainability in this context as an ability to meet the needs of the present generations without compromising the ability of the future generations to meet their own. So for us, it's a collective human ability, as is defined inside the original document, to continue desirable status quo longer within planetary boundaries. Now, the planetary boundaries is an essential concept which has been published in 2012 PNAS, wherein essential nutrients for life to sustain have been mapped on their current status of availability on planet Earth. Now, beyond being an ability, it is also about being a capability. You know, when we have the necessary tools to be equipped with in meeting those needs. So essentially, this slide is about perceiving sustainability not as a one-off. Several times in literature, there is a mention of social sustainability, environmental sustainability, etc., etc. And even business calls for business sustainability. We perceive that to be subsuming the concept of sustainability. Sustainability in its entirety is inclusive of the balance across the three dimensions, which is economy, society, and environment, and nothing can be individually perceived. It is the systemic perception of all three together that should be considered as sustainability, as an ability, a human ability, and a collective human ability, rather than a piecemeal approach. So within our work in Channapatna, where we have studied a lot of craftsmen who are skilled at working on the wood, on the lathe, in making a lot of toys for children, as well as educational items also. We have defined the skill at the craft in terms of several aspects, including familiarity with the materials of the craft, particularly in terms of suitability and workability, knowledge of techniques, skill in the use of tools and appliances in working, which is the general understanding, but there are several other aspects of the skill, knowledge of the necessary science calculations and geometry involved in preceding features. Now, this is expected when the craftsman is given a drawing to be actually realizing it as a product. Familiarity with related crafts, particularly at points of junction or overlap, which is required in conceiving new parts or replacement or alternative parts from another craft into this craft. Knowledge of the industry of which craft is a part, possession of character qualities of integrity, resourcefulness, and determination, coupled with the ability to respond intelligently to constantly changing requirements. Now, those requirements change because craft has been there since a long time. And over the studies, it has been proven that the lack of product diversification is one reason why craft is not being able to attract markets. So when we target product diversification, there is a change that is involved inside something which has been routinely done. Now that, if is not happening, then the craft will suffer. So this motivation, unlike the one which is largely put inside the paper, comes from the market. Now, the context of the article in which we have written, this article is about how that motivation should come from within, so that the concept of sustainability through the handicraft can be self-motivated. So we'll be presenting about that in a short while. And the last part of the skill is constantly changing circumstances as it proceeds, which is actually covered because of the mistake of the bullets over here. I regret that. So some of the observations from the Nallapaneni Art Craft cluster is we did a comparative study of what is unique to this craft cluster with respect to others in the other Indian states of Punjab, Rajasthan, and Uttar Pradesh. And we've studied the products which are outcomes of these clusters, types of materials that are used over there, and then the design features or motifs and identity features that are about these craft clusters. And we also studied the artisans in terms of the scale of their setup, whether it's the individual artisan working on pieces of wood to carve out toys at his house, or it's a small scale setup where there are 2 to 8 people involved doing this, or a medium scale effort. So the aspects across which we've studied the artisans are lathe availability, type of lathe, chuck hold, training level, financial support, work category, peak season, off season, in season. Wood used, colors used, willingness to try new products, and whether the designs were previous samples or whether they were sketches or samples created from sketches already. Several other factors were also considered to compare individual artisans, small scale setups and medium scale setups, so that we can understand the context in which the artisan or the craftsman operates at whatever skill level he or she is. We also did a study on why consumers buy products from Nallapaneni, and the factors that we have come are for their economic pricing, for their eco-friendliness, for their colorful look, and for their shape. Most of these toys are axisymmetrical in shape. They are turned on the lathe, and they have been like that since a lot many years. So based on this, we have ranked the intentions, and the colors has come out to be the first reason why consumers buy these products, and the shape of the products came second, and the economical pricing came to be third. Surprisingly, eco-friendliness came fourth. We also wanted to see why people didn't prefer these products. So we also spoke with people who have not bought any of the products on sale, and in their opinion, the products lack freshness and fun, and some of them already have similar looking products, so they've not bought those. And the others said there are other craft clusters which make better products than what is currently over here, or same products. So lack of freshness and fun is also a reason why these products are not being bought. And in comparison with the intention of the buying, we might want to make a good case. So from the expectation point of view, when we did our consumer studies, we have understood that the consumer should be provided more ranges in form and appearance. Symmetric form makes new design look repetitive. So even though the design is new, if it is symmetric, it will be perceived that it is about the same craft and it is nothing new. And it might lack that fun or freshness aspect which has been identified earlier. Symmetric form has been explored adequately, and any further experiment in symmetricity would be considered routine. Eccentric forms in lathe would bring excitement in design. The craft should penetrate new markets like corporate wear. The craft should also explore new designs for the market. And the craft should explore new techniques of wood lathe. So these are the expectations that we have come up with for this craft at Channapatna, so that its own sustenance is not in question. So these are some of the outcomes, and there's only one part of the study, and we couldn't do more aspects of the study, which is for future work, and we will be glad to be presenting it to this audience at a later time when our study is complete across all the questions of research questions that we have. For now, we have tried out a new technique of eccentric turning using the wood lathes, existing wood lathes of the craftsperson, by designing a attachment which performs eccentric turning. And these are some of the forms that the craftsman could turn using this attachment. Now, in terms of them being unique, everything is distinct. When the distinctness of the axisymmetric forms, which were earlier being done, vary only in one direction, which is along the axis, or rather perpendicular to the axis. Eccentric turning allows the uniqueness to be expanded manifold. So what you're seeing here are very interesting objects which are not usually found in lathe turn toys, and these have been produced as consumer products also. What you're seeing right now are experimental explorations, and some of them have been purposely made to be flower vases, etc. This is a Scotch tape dispenser, which is a sellotape dispenser, which is also made on the eccentric turning technique in the form of a snail. And this is a pin-up holder made for the markets outside India, this being an edge jog. And the other part of the study is with respect to the skill perception, the attitudes of the craftsperson, and their perception of introducing new techniques as a technology or an addition in terms of understanding the reception they have for this towards being able to do what they've been doing much better. So the article touches on the concept of self-reliance, which is reliance on one's own powers and resources than those of others. So it's largely centered around the craftsperson, whether he's working individually or inside a small scale setup or a medium scale setup. So when it comes to self-reliance and craftsmanship, what we mean is the amount of self-worth that the craftsman derives from his own work, and his own work now being perceived from the context of introducing of new technologies also, that is helping him explore further directions within his own family craft, right? So we have surveyed craftsmen, and they were very happy to try out the eccentric turning as a new addition, resulting in interesting outcomes. And due to the earlier craftsmen performing routinely in the way they did, and with this new technology, we are also hopeful that this motivates further craftsmen to actually try out this technology and then survive the craft longer. So as all of these attempts of trying something new, although someone is already skilled at doing whatever is routinely done, is an attempt of pushing the craft a bit further. And then when everybody is challenging themselves at their own pace with these new additions or interventions, we foresee that the craftsmanship reaches new heights when individual craftsmen progressively keep pushing their limits to achieve further than what the previous one has done or their contemporaries or peers are doing. So the entrepreneur of people in their productive years is hence directed towards controlling means and conducting oneself better and better with lesser and lesser resources. This is also important, particularly from the fact that the amount of resources that craft consumes, although less, can be lesser, particularly again from the point that the markets are very much increasing, growing at an average rate of 10 to 12, 10 to 15% all over the world. So if you contrast this with an economy-centered outlook for the sustainability aspect, some of the recent examples or even old examples that we have are development that comes with pollution, as has been highlighted by environmental Kuznets, or the scientist named after the scientist Thomas Kuznets. Industrial primacy comes with human rights abuses, which is the G7 concerns. We've seen Wall Street protests, and we've also seen the vaccine booking race, despite COVID being a global humanitarian urgency, highlighted by WHO's authorities very recently and ongoing. Growing disparity between the rich and poor, tax abuse and political preference in the developed world, and U-turns in climate protocols. So, economy-centered approach trumps sustainability in principle, as it is not a human-centered approach. Now, I would like to intimate, or rather tell everybody, that sustainability in principle is axiomatic. And when we say axiomatic, what I mean is that there is no founding of the principle of it being human-centered, right? It is an anthropocentric concept. Why? There's no reason. It's just axiomatic. So when it is axiomatic, there is more reason why we need to be bothered about the human first, right? Once we subscribe to it in entirety. I should also add that systems as relevant to understanding sustainability are so huge and vast that they're complex and they're not observable. And when they're not observable, tracking their progress or even claiming improvement in them becomes difficult or even impossible. So when observability has not been established, and when the concept of sustainability is axiomatic, the closest way that we can actually claim to be still sustainable is being nearest to the concept of anthropocentricness or human-centered interventions. So from that perspective, even when we talk about exports, etc., these are all economic centered. But when we talk about the craftsman, who is at the axis of generating the object of the entire system around the handicrafts, is very important, or becomes very important. So if you could see the way in which the three dimensions of sustainability could be discussed across this area, it'll be like this. When handicrafts are the focus of sustainability across the economy, it is increasing contribution to the economy, which is 12 to 20% annual growth. Handicrafts provide employment to approximately 7 million artisans alone in India, and they provide low-cost, high volumes with decentralized distribution systems. Economy, increasing domestic demand of aspirational middle class will continue to provide sustenance beyond dependence on exports alone. So there's a healthy market within to actually cater to, so that there's this close to 7 million artisans can actually benefit from getting employment. When it comes to the society, it provides employment to millions within their family occupation, which is very motivating and increases self-confidence, continuously get better at one's work. The rural to urban migration, which is a global problem, can be reversed when we provide well locally rather than concentrating employment inside urban centers. Involvement of the family occupation improves skill, self-respect, and drives the virtuous loop for providing high-cost, low-volume, customized work achievements also. So if you see the handicraft systemically, the handicraft sector systemically, there are several influences. And several of these influences drive vicious loops, which drive down the handicraft sector's output. However, when we work it out from within, inside out, with the goal for generating more and more handicrafts taken inside within the craftsman to be self-motivating, it'll be driving a virtuous loop, and sooner or later, the production volumes for the handicraft can be much higher, with demand and the quality of the products coming out being much better. When it comes to the environment, the materials that are naturally sourced are predominantly the cases with the different types of handicrafts products that we are making and exporting. Emissions and pollutants are not concentrated as production is decentralized. Endeavor to utilize resources fully reduces waste and drives a virtuous loop of involving with the material to get the maximum out of it. It will become the entire focus of the artisan or the craftsman himself to actually get the max out of the minimum. But that's a very good way forward when we're talking about reducing material consumption. So finally, the arguments in favor of handicraft and sustainability are the axiomaticness of sustainability. The involvement is best if driven out of work and self-motivation. The work should be self-determined and hence self-motivated. Handicrafts provides the best case of personalization that every individual aims for in terms of customizing the products for themselves rather than buying one off the shelf of the mass-produced goods. And the ongoing trend suggests that the existing producer base will not be able to cater to the aspiring needs of the middle class. So the sooner we actually meet this in terms of encouraging producers to produce as much as is needed, it'll be good. However, if we don't inculcate the criteria of doing or churning out these products as an exercise, a self-motivated, self-determined exercise, it will soon result in a lot of material waste. So from that perspective, when artisans act in a self-determined and self-motivated way, they churn out the best which is representative of them, increasing the adoption of handicrafts longer. So this means sustainability of the handicrafts themselves, as well as the system that is entirely involved, directly or indirectly around it, to sustain longer. So that is the case for handicrafts, for sustainability through self-reliant craftsmanship. So I would like to revisit the first, one of the first slides that I have put. So in effect, we are actually trying to enlarge the wheel, although we are not trying to enlarge the material through it, because the endeavor here is to improve the skill of the person, right? And that doesn't happen overnight. So we are inside, we situate the goals of coming out with delightful crafts as an endeavor of the craftsman, as a progressive endeavor of the craftsman, wherein he gets involved in one part of the exercise of realizing the artifact slowly, right? So that includes controlling the speed of the wheel, not of the potter, but of the circulation of matter through this entire system, and putting an end to the material consumption towards reducing the quantities slowly and slowly. So those are some of the references that we have used for this work. The work is not complete yet, and I thank all of you for your attention. I wish I have further opportunities where we could complete our work and then present it to the same audience for your better understanding. Thank you all for your time.